In the last lecture, we were examining unidirectional transport, oscillatory flow in a pipe. So, the configuration consisted of a pipe of radius r and the velocity at the wall of the pipe was equal to 0, and we applied a pressure gradient across the ends of the pipe that was an oscillatory function of time with frequency omega or with time period 2 pi by omega. And then we wanted to know what is the velocity profile in this pipe, okay, due to this oscillatory flow. So, we had scaled the radius by the radius of the pipe and used omega t for the time scale, for the scale time. Okay. And the equation for the momentum equation for this unsteady but fully developed flow. Okay. Unsteady means it is a function of time, the velocity is a function of time. Fully developed means the velocity is not a function of the downstream coordinate, okay. It is not a function of the axial coordinate x, it is only a function of the radial coordinate, and the only non-zero component of the velocity is Vx. Okay. So, that is the only non-zero component of the velocity in this case. So, because of that these two terms, the convective terms in the differential equation, both of them are 0. Okay. And the diffusion, the streamwise diffusion is also 0. Okay. And we are left with an equation rho times partial Vx by partial t is equal to minus partial p by partial x plus mu by r d by dr of r partial Vx by partial r. Okay. So, that is the differential equation for the velocity field. Okay. And the pressure gradient was of the form k cos omega t. Okay. The pressure gradient was of the form k cos omega t or cos of t star. So, based upon the equation, so we substituted that into the equation and divided throughout by k, and based on this we got two possible scalings for the velocity. Okay. One is a viscous scaling, okay, based on viscosity, the other is the inertial scaling based on fluid inertia. Okay. We selected the viscous scaling in this particular case. Okay. And on the left side we have this parameter, which is the Reynolds number based upon the frequency of oscillations and the pipe radius. Okay. And on the right side I have the pressure gradient term, okay, which is now sinusoidal, and the viscous term. Okay. Cos t was written as cos of t star is equal to the real part of e power I t star. Okay. And we had written an equation for Vx plus. Okay. We had written an equation for Vx plus, okay, with this forcing. Okay. Re omega partial Vx plus by partial t star is equal to minus e power I t star plus plus 1 by r star d by d r star of r star partial Vx plus by partial r star. Okay. So, this is an auxiliary equation, a complex equation with a complex forcing here. Okay. The equation for our velocity field, okay, the equation for our velocity field is the real part of this equation. Okay. The equation for our velocity field is the real part of this equation. Therefore, the solution for our velocity field is also the real part of the solution for Vx plus. Okay. The solution for our velocity field is also the real part of the solution for Vx plus. Okay. So, that is the velocity. Okay. And further, if the forcing is sinusoidal with a particular frequency and the equation is linear, then the response also has to be sinusoidal with that same frequency. Okay. If the forcing is sinusoidal with a particular frequency and the equation is linear, the response, forcing in this case is the pressure gradient, response is the velocity that is generated due to that pressure gradient. So, the forcing is sinusoidal, then the response also has to be sinusoidal and it has to have the same frequency. Okay. So, therefore, we had written Vx plus as the real part of a function of r times e power I t. Okay. And based upon that, we had got an inhomogeneous equation for this Vx tilde, okay, with boundary conditions. The velocity is 0 at the wall, the slope is 0 at the origin, okay, and we had solved that. Okay. Inhomogeneous equation, we had separated out into a general solution plus a particular solution. General solution satisfies the homogeneous equation with the inhomogeneous term on the right side set equal to 0. Okay. General solution satisfies the homogeneous equation with the inhomogeneous term set equal to 0. We got that in the form of Bessel function. Particular solution is any one solution that satisfies the inhomogeneous equation, okay, and the simplest solution we got was a constant. So, based on this, we had got a solution for the velocity field. Okay. We had got a solution for this complex part, okay, for this complex amplitude of the velocity field. Okay. So, this was the final solution that satisfied all the boundary conditions. From this, we get Vx plus is equal to Vx star tilde e power I t star, and the actual velocity that we had originally wanted to solve for is the real part of this Vx plus, which is real part of Vx tilde star e power I t star. Okay. So, you can do all of these calculations and get the velocity fields. Okay. Clearly, the velocity field is going to be a function of only one parameter, that is the parameter r e omega in the problem. That is the only dimensionless parameter. Okay. Note that this I r e omega is only parameter in the equation and the boundary conditions are homogeneous. The velocity at the wall is 0, at the axis the derivative of the velocity is 0. Okay. So, the boundary conditions are homogeneous. Therefore, the velocity field depends only upon this one parameter, and then we can plot the velocity field, okay, for different times along the sinusoidal variation of the pressure, okay, dp by dx. Okay. It has a sinusoidal variation, okay, and I can consider this at different positions along the sinusoidal variation. Okay. If you consider a small value of r e omega, if you consider a small value of r e omega, and if I plot, okay, if I plot Vx star, okay, as a function of r star, okay, all the way from r star is equal to 0 to r star is equal to 1. Okay. At r star is equal to 1, you know that the velocity has to be 0. Okay. So, as the pressure goes back and forth, the velocity will also go back and forth. Okay. And the velocity has this form. Okay. So, at this particular point in the cycle, okay, the pressure gradient is positive, that means that the velocity has to be negative. Okay. If I take a small value of r star, okay, if I take a small value, okay, 0.1 say, if I take a small value of r e omega, okay, then the pressure at this point, okay, at this point you get something that looks close to a parabolic velocity profile here. Okay. If you go to this point, it is positive and you get something that looks like this, parabolic, nearly a parabolic velocity profile, when this parameter r e omega is small. Okay. And then at this point here, you get something that is sort of almost flat. Okay. And then here, okay, at this point, you get something that goes like this. Okay. And finally, at this point you get something, the pressure gradient is negative and therefore, the velocity is positive. You get something that goes something like this. Okay. Okay. So, these are the kinds of velocity profiles going back and forth that you get as part of the cycle when this parameter r e omega is small. On the other hand, when it is large, at this point here, when the pressure gradient is positive, right, you get a velocity that goes almost close to 0, and then it goes out and comes here like this. Okay. At this point it is still positive, but the velocity profile looks somewhat different. Okay. So, the velocity profile looks something like this. Okay. And at the point where the pressure gradient is equal to 0, you find that there is the maximum velocity. Okay. You find that there is a maximum velocity. Okay. And then it comes backwards. Okay. So, at this point you get a velocity profile that looks something like this. Okay. And at the yellow point you get a velocity profile that looks something like this. Okay. And then it goes on the other side as part of that cycle. Okay. This is when Re omega is equal to 100. Okay. So, you can see that the nature of the velocity profile is actually very different in these two cases. Okay. The nature of the velocity profile is actually very different in these two cases. Is there a way to physically understand this? Okay. So, is there a way to physically understand this? What is the meaning of the limits of low and high Reynolds number? Okay. You can see that at low Reynolds number the velocity profile is almost parabolic, whereas at high Reynolds number the velocity profile shows a very different shape. It is actually close to 0 when the pressure is at a maximum, and it goes to a maximum when the pressure gradient passes through 0. Okay. So, why is that, and can we understand that? So, first let us consider the low Reynolds number limit. Okay. Note that the equation was of the form I Re omega Vx star is equal to minus 1 plus 1 by R star okay. Now, if this Re is small, right, if Re were 0, then that term would, the left side would be 0 altogether, there are no inertial terms. Okay. In the limit as Re is small, we can expand. Okay. In the small parameter Re omega. Okay. Since this parameter is a small parameter, we can expand in the small parameter, substitute into the equation. Okay. Substitute into the equation. Okay. So, I will get plus etcetera, that is the left side is equal to minus 1 plus 1 by R star expand the left and the right sides, okay, and collect terms of equal powers of Re omega. Okay. So, for coefficient in this equation of Re omega to the power 0, okay, is what? The left side I have coefficient of Re omega power 1. Okay. So, the only coefficient of Re omega power 0 is minus 1 plus 1 by R Next, coefficient of Re omega is equal to 1. Re omega power 1. Okay. On the left side, the coefficient of Re omega power 1 is Vx naught. Okay. So, I will get I Re omega Vx naught is equal to minus 1. Sorry, there is no coefficient of Re omega power 1 on the right side. Okay. This term here, this inhomogeneous term here is order 1. Okay. It is order Re omega power 0. Okay. So, there is no, therefore, there is no coefficient of Re omega power 1 in the inhomogeneous term. Okay. It is only in this velocity that we have this term here. Okay. So, I get 1 by R okay. Similarly, you will have coefficient of Re omega square. Okay. I am sorry, I should not have Re omega here because it is already a coefficient of Re omega. Okay. On the left side, Re omega square, the coefficient is Vx1. Okay. So, I will get Vx1 is equal to 1 by R on the right side, the coefficient of Re omega square is Vx2, okay, and so on, okay, and so on. So, you can expand this up to any order. Okay. I have expanded only up to the first two orders. Okay. I have expanded the equation and now I have to expand the boundary conditions as well. Okay. So, therefore, at R star is equal to 0 and at R star is equal to 1. We know that Vx star is equal to 0, which means that Vx naught is by dr star is equal to 0. First order dVx1 by dr star is equal to 0, dVx2 by dr star equal to 0. At R star is equal to 1, Vx naught is equal to 0. Okay. So, I can solve each of these equations subject to their respective boundary conditions. Okay. So, I can solve the first equation in order to get what is Vx naught. Okay. And note that Vx naught appears as an inhomogeneous term in the boundary condition for Vx1. So, once I have solved the first equation, I know what is Vx naught, substitute it into the second equation, find out what is Vx1, substitute it into the third equation, find out what is Vx2 and so on. Okay. This goes by the name of a regular perturbation expansion. Okay, this goes by the name of a regular perturbation expansion. Okay, so, I can solve order by order what is the solution. So, if I take the coefficient of Re omega power 0, I get minus 1 plus 1 by R this is equal to 0. okay, subject to the boundary condition that the slope is 0 at the center and the velocity is 0 at r star is equal to 1. Okay. And this gives me a solution, that is V x naught is equal to minus of 1 minus r star square by 4. Okay. The second equation, that is I r e omega V x naught is equal to 1 by r d by dr r dv x naught by dr. Okay. Okay. There should not be no I r e omega because I am taking the coefficient of I r e omega. So, I am taking this equation. Okay. I am taking this equation subject to the boundary conditions. Okay. Subject to the boundary conditions. Okay. This can be solved now because we know we just substitute V x naught over here. The solution for V x naught is substituted over here. Okay. And I will get V x 1 is equal to minus I into 3 minus 4 r star square plus r star power 4 by 64. Okay. And like that I can solve the next equation. Okay. V x 1 is equal to 1 by r d by dr of r dv x 2 by dr, subject to boundary conditions of course. Okay. R is equal to 0, velocity is 0 at the wall and velocity is slope is 0 at the center to get V x 2 is equal to divided by 2304, okay, and so on. Okay. So, you can do solution term by term here. Let us examine what this first term is. Okay. Let us examine what this first term is. Okay. V x naught, okay, is equal to minus of 1 minus r star square by 4, okay, which implies that the velocity, scaled velocity plus is equal to minus of 1 minus r star square by 4 into e power I t star, okay, which means that V x star, okay, in this approximation is equal to minus of 1 minus r star square by 4 into cos of t star. And I had used the viscous scaling, therefore, V x will be equal to k by k r square by mu, okay, into V x star. Okay. I had used that scaling. This is equal to minus k by 4 mu, okay, into r square into 1 minus r by r the whole square into cos of t star. Okay. I can write this as minus k by 4 mu r square minus r square cos of omega t, because cos of t star is cos of omega t. So, this expression for the velocity, okay, this expression for the velocity is of course time dependent because of the presence of this cos t star. But if you realize that dp by dx is equal to k cos of omega t, okay, so that I can combine this term with the k here. Then I get the velocity profile as minus 1 by 4 mu dp by dx into r square minus r square. This is the same as the parabolic velocity profile in a pipe for a steady flow. Okay. So, this is the same as the parabolic profile in a pipe for a steady flow. Okay. What this is telling us is that as the pressure is varying with time, okay, as the pressure is varying with time, okay, as the pressure is varying with time, at each instant the velocity profile in the pipe is the same velocity profile as you would have for that particular value of that pressure. Okay. At this point it is lower and it passes through 0 here and it goes the other way as well. Okay. Okay, you are getting the same solution as you would have got for a parabolic flow for a steady pressure gradient, right. For this particular oscillatory pressure gradient, the solution is the same as that for a steady pressure gradient with that instantaneous value of the pressure gradient at that point in the cycle. Okay. Now, why is that? Okay, so, let us look physically at what is happening. So, Re omega I had written as rho omega r square by mu. Okay. I can also write this as rho r square by mu into 2 pi by the time period of oscillation of the pressure cycle. Omega is just 2 pi by t, okay, 2 pi by the time period of oscillation of the cycle. Alternatively, I can write this as r square by the kinematic viscosity into 2 pi by t. Okay. R square by kinematic viscosity, okay, r square by nu is equal to the time required for momentum diffusion across a distance r. Okay. R square by nu is the time required for momentum diffusion across a distance r. Okay. So, therefore, this Re omega can also be written as the time required for momentum diffusion across a distance r divided by the time period of the oscillation into 2 pi. Okay. It can also be written as the time required for diffusion of momentum across the distance r divided by the time period of oscillation into 2 pi. What is the limit of low Re omega? Okay. The limit of low Re omega is where the diffusion time is much smaller than the time period of the oscillation of the pressure. That means that momentum diffuses across the entire pipe over a time scale small compared to the time period of the oscillation. So, at each instant in time the momentum is diffusing instantaneously across the pipe. Okay. At each instant in time momentum is diffusing instantaneously across the pipe for that particular instantaneous value of the pressure gradient. Okay. And therefore, this implies that at each instant in time the momentum diffusion is instantaneous. That means, you are getting the same solution as you would get for a steady flow, because at each instant in time that momentum diffusion is an instantaneous process. Okay. So, that is the limit of low Reynolds number when the diffusion time is small compared to the time period of oscillation. And because momentum is diffusing instantaneously, you are getting the same solution as you would get for a steady flow, a parabolic profile with maximum velocity corresponding to that instantaneous value of the pressure gradient. Okay. The maximum velocity is varying as a function of time. It goes as proportional to cos omega t. The maximum velocity at an instant in time is the same as that for a steady flow with the pressure gradient given by that value at that particular instant in time. Okay. So, this happens when the diffusion time is much smaller than the time period of oscillation. Limit of low Reynolds number. Okay. What happens in the opposite case where we have the limit of high Reynolds number? Okay. I will continue that in the next lecture. Okay. What happens in the limit of high Reynolds number? I will continue that in the next lecture. I will see you then.